This is the third part of Lesson 11. In heat transfer, in Lesson 11, we have been looking at how to analyze steady-state, multi-dimensional conduction heat transfer problems. In the previous lesson, we focused on how to properly create a numerical mesh. In this lesson, we will look at the derivation of the governing equation for heat transfer for an interior node in the mesh. By the end of this lesson, you should be able to follow the steps required to derive the governing equation for an interior node in the numerical mesh. In the following lesson, we will take a look at deriving the equation for a node on the boundary of the physical problem. On with the lesson. Recall that a finite volume analysis is conducted in 3 steps. The first step is to discretize the domain by creating the numerical mesh. The second step is to derive the governing equations for each volume in the mesh. And then the final step is to solve the governing equations that are coupled together. In this lesson, we'll be working on step 2, deriving the governing equation for the volumes in the mesh. And in particular, we'll be looking at a volume coincident with an interior node in the mesh. On this slide, we have depicted an interior node in a numerical mesh. The volume associated with the node is indicated in red. This is a 2-dimensional mesh. The volume has 4 faces. The mesh spacing is such that the distance between node points in the x direction is delta x, and the distance between node points in the y direction is delta y. Because faces are located midway between node points, this means that the length of the top face of a volume is also delta x, and the length of a vertical face of the volume is also delta y, equivalent to the node spacing. For convenience, we will replace the node indices m and n with letters corresponding to cardinal directions. I find it easier to think through the problem using these cardinal directions. The node of interest will be labeled with a P. The node to the west of this point P is labeled with a W. This is equivalent to moving west on a map. The node to the east will be labeled with E, the node to the south with S, and the node to the north with N. As a reminder, these are the indices M and N associated with each of these nodes. The node of interest is the MN node. For example, the node to the north is the MN+1 node. It is 1 row above. When deriving the governing equations for heat transfer in the finite volume technique, we will assume that the heat transfer is in across each face. We make this assumption because we do not know before the problem is solved what the direction of heat transfer is. In this approach, if we ever calculate a negative value for the heat transfer, it means that we have drawn the arrow in the incorrect direction, and heat transfer is actually out of the volume. I have labeled the heat transfer across each face of the volume. There is heat transfer across the west, east, south, and north faces. These heat transfers are denoted by Q sub W, Q sub E, Q sub S, and Q sub N, respectively. Finally, one of the advantages of numerical techniques is the relative ease with which complexities such as thermal energy generation can be handled. We have thus assumed that there is also a uniform generation of thermal energy within the volume, denoted by Q triple prime delta V. We now apply the heat transfer energy balance equation to the volume. because we are interested in steady-state heat transfer, the energy storage term becomes 0. And because we have assumed that all heat transfer is in, there is no energy flow out across the faces of the volume. This term also becomes 0. We now substitute for all of the energy flows in. It is the conduction heat transfer across each of the 4 faces, and also for the thermal energy generation. We now have the following equation from the energy balance. The next step is to apply Fourier's law for the rate of heat transfer by conduction. We are substituting in Fourier's law, which provides an equation for the flux across the face times the area of the appropriate face. For the conduction heat transfer across the west face, Fourier's law says minus the thermal conductivity times the temperature gradient at that face times the area gives the overall rate of heat transfer. A similar substitution is made for the heat transfer across the east, south, and north faces, respectively. Here is the equation repeated. We must now say something about the temperature gradient at each of the faces, as the temperature gradient is the key part of Fourier's law. Because we are applying a finite volume analysis, we are allowed to choose any interpolation profile for the dependent variable between the node points. The dependent variable of interest to us in heat transfer is temperature. It will be easiest to assume that the temperature varies linearly between each node. This assumption allows us to calculate the temperature gradients at the west, east, south, and north faces. An assumed linear variation of temperature from the west node to the P node means that the gradient at the west face can be calculated according to the following. We take the difference in temperature divided by the spacing between the node points. The spacing between the node points is delta x. By a similar argument, the gradient at the east face is T minus Tp over delta x. We note the negative value because the heat transfer is down the temperature gradient. In the south and north faces, the node spacing is delta y rather than delta x, but a similar approach is followed here. If we substitute these temperature gradients into the governing equation from the heat transfer energy balance equation, we are left with the following equation. We have replaced the temperature gradients with their appropriate definitions, assuming that the temperature is very linearly from node to node. Here is our new equation. The next step is to substitute in for the areas of the faces and the volume, relating these areas and the volume to the mesh geometry and the spacing delta x and delta y. Looking at the area associated with the west face is the area of this vertical line. The area is delta y times the depth into and out of the page. However, since we are conducting a two-dimensional analysis, there is no depth, and we can set the depth to be a unit value of unity 1 meter. So the area of the west face simply becomes delta y times 1. Similarly, the area of the east face is also delta y times 1. The area of the south face is the nodal spacing delta x times 1, and the area of the north face is the nodal spacing delta x times 1. The volume is delta x times delta y times 1. Stated simply, it is the length times the width times the height. We assume 1 meter depth into and out of the page. With these substitutions, the finite volume equation becomes the following version. The areas have been replaced by their appropriate definitions, as well as the volume. If we employ a numerical mesh in which the nodal spacing in the x and the y directions are equal, then we can further simplify the governing equation. Here I have noted this equivalency. And because of this, the delta x and delta y cancel each other in each term. And in the thermal energy generation term, delta y times delta x simply becomes delta x squared. If we divide this equation by the thermal conductivity K, we are left with the following equation. Notice that there is common Tp here, and there are 4 of these minus T sub p. Combining these 4 minus T sub p together gives the following equation. Using the cardinal directions, this is the finite volume equation for an interior node. But it's handy at this point to substitute back in the nodal indices associated with the west, east, south, north, and volume of interest nodes. We simply make the substitutions based off of our reminders of what these cardinal indices represent. We have now derived equation 4.35 from your textbook. This equation applies to any interior node in the mesh in which the nodal spacing and the x and the y direction are equal, and the thermal conductivity and thermal energy generation are constant values. In the next lesson, we will derive the governing equation for a boundary node.